our next speaker today is Michael Wilde, who is a lecturer at the University of Plymouth. And he's going to be providing us with an update of some work we've seen from him in the past at this workshop. So we really appreciate that. And it's on breath metabolite networks by GCGCMS and changes during recovery from acute respiratory exacerbations. Thank you, Michael.
So good morning, everyone. It's really good to be back. As Kate said, I missed the MDC and the symposium last year. So I've come back this year to sort of give you an update on some of the really exciting stuff we've been doing with GCGC breath data and some of the really interesting structure that we've seen in the data. So before I start, I just want to acknowledge the group of fantastic scientists that I work with, particularly in the EMBER consortium, especially Rebecca Cordell and Dr. Matt Richardson. So I'm going to make the assumption that most of you are familiar with this concept of exhale breath analysis and using exhale VOCs as a potential new non-invasive diagnostic. And if we look at this recent tree map from a very recent review, we can see that breath diagnostics has been primarily used in cancer, especially lung cancer. And that's not surprising, right? Consider we're doing a bit of a risky new venture and you want to make maximum impact as possible. If you look at non-cancerous pulmonary disease, you can see then it's being primarily used in asthma and COPD. And then after that, it's only really tuberculosis and cystic fibrosis, which make up 4% combined. And it's perhaps not surprising that we see COVID-19 now entering the top 10 pathologies being studied. To date, a range of individual biomarkers have been reported. However, the excluding sort of permanent gases like pheno and isotopically labeled CO2, the clinical translation of VOCs into clinic has really been held back behind this wall of inconsistency. And most people blame the analytical method, lack of standardization and analytical methodologies, which is important, but it really also comes down to trial design, trial outcomes, and really the inconsistency in the panel of markers that are being reported. And perhaps we can better understand this inconsistency if we consider what we expect a breath-based biomarker to be. So I think it's sort of well established in the community now that a single unique chemical marker in breath it just doesn't exist for that we're chasing unicorns if we think that's going to happen. But perhaps we should also now be moving away from this idea that we can reduce the breathome or any metabolome really down to just a handful of 1 or 5 sort of individual metabolites. Because considering the complexity and the variation, that's going to be very difficult to sort of validate in many cases. The exception to that, though, would be microbial VOCs and studies looking at infection, I guess. So others are now sort of advocating that we move towards this signature or using multiple VOCs in tandem to build up a breath print, and then perhaps in alongside non-VOC measurements such as lung function tests as well. And so you're building up this picture of complexity. And I think the data that we present today goes several steps further. And so I'm going to be presenting the identification of a really diverse score of VOCs, and it really reflects the complexity of the breathome and also challenges what we expect from a breath-based biomarker. And that's really only been made possible through the use of GCGCMS. So we're very fortunate to be able to publish our VOC signatures associated with acute exacerbation. And I took it as a personal win and also a win for the GCGC community to get a GCGC chromatogram in Science Translational Med, which was really fantastic. And so today I'm going to comment very quickly on the sort of signatures of acute disease. But I would then want to move on to a second, perhaps more important discovery, which was the identification of these metabolite sets, which is primary evidence of these breath metabolite networks that we're seeing in breath, which is important because it perhaps overcomes the inconsistency that we're seeing in the biomarkers being reported. And then very quickly, if I don't bang on for ages, we might be able to get onto the validation of these metabolite sets as we look across a longitudinal cohort. So very quickly then moving on to covering what the signatures were that we identified. So we did an acute study, and the primary question was, can we use VOCs and breath to differentiate acute breathlessness at triage? And so patients came in acutely breathless to hospital, and we sampled them within 24 hours of admission. This acute study included just shy of 300 patients across acute asthma, COPD, heart failure, and pneumonia, and then we also had age-matched healthy controls. And then that led to this secondary aim, which admittedly we weren't really powered for, which was, can we identify VOCs associated with those subgroups as well? So we did this using multidimensional gas chromatography. We used 5MS in the primary and then a wax in the secondary, with a split between the MS and FID using a flow modulator. And this is what a typical breath chromatogram would look like. And you'll notice that I use the word visualization here as opposed to separation. To the purists in the room, that might make your toes curl a little bit, but we found the clinicians, they love this idea of being able to image breath. Clinicians love imaging everything, CT scans, MRI, x-rays, and things like that. And so we sort of sucked it up and we were just like, hey, whatever gets GC into sort of routine clinical analysis. The way we delivered this was, it was really nice to see that others we're not far off in what we're doing here. We've been running discrete analytical batches since 2017. We do this in all the studies to keep our data comparable throughout. So we run N-alkanes and aromatics. We then run the samples in small batches of 6, followed by like 2 independent external standards, so 52 different VOCs afterwards, as a sort of external match and control of the situation. And I think I included it there. We saw, post-alignment, we saw really small variation over sort of 2,000 samples over 2 years. So sort of the challenge that James was describing earlier, which was really, really neat. I'm not going to spend too much time on the workflow because you can see I'm trying to get to the data. But basically, this is the workflow. And what I want to say here is that data reduction is a really crucial part of any chemometrics workflow. However, we're always at the risk of throttling our data to the point where we reduce the number of features down to where we're impacting the discriminatory power and the point of analyzing the metabolome and using GC in the first place. So we selected a couple of penalized regression models to introduce sparsity in the data and try and minimize that inevitable overfitting, which you typically see. And so we ended up with 101 features associated with these different subgroups within acute breathlessness. And we could use the penalized coefficients to produce a biomarker risk score. So not too different to what they do in like GWAS studies. And we applied exactly the same model to our air supply and background samples, and we only had 2 overlapping stable features. So I think that really speaks volumes about the rigor in the sample collection that we use. GC afforded high level confidence in compound identification. So we had 60 of the 101 against pure standard. We actually had 84 against pure internal standards, but 60 of the most interesting ones. And then we had 20 to MSI level 2. So that's 80% of 101 features that we had very high confidence of what we knew that compound was. And because we used GC, we had everything else MSI level 3, because even though we didn't know what hydrocarbon it was, we knew it was a hydrocarbon or a branched hydrocarbon. So very quickly then, the cohort was split into discovery and replication, and we got reasonable sensitivity and specificity in the replication cohort. And if you break that down based on the individual subgroups, which we weren't really powered for, you can see the specificity is maintained, but the sensitivity drops off. And this is perhaps not surprising, really, considering we're comparing acute with acute, not acute with healthy, but acute with acute. And so we're trying to diagnose someone with a cough with someone else with a slightly different cough. So they share systemic inflammation and metabolites. I'm missing a slide. So I think that slide said something along the lines of, So this is pretty much the point where most breath studies get up to. We get a panel of biomarkers that we're going to report, and we identified hydrocarbons and aldehydes, and so we sort of tentatively relate that to oxidative stress, and that's where we get to. And what we wanted to ask of the data is, can we go further than this? Is there something we can get out more that shows a response that these VOCs are absolutely related to acute exacerbation, for example? And so, forgive me if I miss anything on that slide, but we're going to move on. And so we cannot assume statistical independence among metabolites. So if we're seeing lots of hydrocarbons, we know they're coming from perhaps the same mechanism. So we actually expect them to be correlated. So then the statistical independence among metabolites is incorrect. And however, pathway analysis is not applicable in this case. So metabolic databases, okay, they're okayly annotated, but relatively speaking, they're poorly annotated. And breath volatile metabolite databases are even worse. So they're not annotated, really. And so how can we sort of take that step from sort of correlations to seeing something more structural in the data? And so we used metabolite set and chemical similarity enrichment analysis, which was inspired by the work of Dinesh Barapul and Jeremy Ash. And so what does that mean? That means we have, so if you, each yellow blob is a VOC, so one of our 101 VOCs, and so you can generate a raw p-value and your fold change for each one of those VOCs. You can then define metabolite sets by doing some clustering. And then for each one of those metabolite sets, you've got the p-value. You can use the KS test to generate a set level significance. So is that set of that group significantly up or down between groups? And because from GCGC we had high confidence about the VOC structures, we could also turn on a set level chemical similarity coefficient using like a Tamanoto coefficient to determine chemical similarity. So now for each metabolite set, we have set level p-value, fold change, and chemical similarity coefficient. You can then plot this against significance with chemical similarity. And so each one of these blobs is a group of metabolites. If they're red, they go up. If they're blue, they go down. If they appear, they're significant. If they don't, they're not. And so from this, we can get data-driven and chemistry-driven information from this breath data. It's all right to plug my thing in? Yeah? Sorry, I can just keep making stuff up as we go along, but...
Just go directly in there.
Okay, so I don't want to go back to the beginning. So sorry about that. So we have these metabolite sets defined by chemical similarity and whether they correlate based on abundance in the breath, and we can start to infer more information from these sets. So if you apply this technique to... Need to... cool, don't worry. If you apply that chemical similarity enrichment analysis to the 101 VOCs, you get a plot like this. So you get some metabolite sets which are significant, which was good. And so if you look at like set 7, for example, you can see it's got high chemical similarity, it is significant, and it's upregulated or elevated in acute disease. And if you want to sort of be a judge of the chemical similarity coefficient, if you look at the members of set 7, I think you can all agree that they're generally highly similar in their chemical structure, I guess. So we get these low molecular weight branched hydrocarbons. And so if you do a hierarchical clustering on those metabolite sets, we can then see certain sets that are significantly enriched in acute exacerbation, okay? And so this was really nice because it shows metabolite sets indicative of disease response. But can we go further? Can we validate this? So then moving on to the objective 2, which was to look at the identification of these metabolite sets, sort of infer then that there could be this sort of breath metabolite network. So most of you are familiar with the concept of a network. Cool softwares for visualizing networks have come about in the last couple of decades. Graph theory goes all the way back to Euler in the 1700s. And then fundamentally, that concept of describing a relationship between two measurements goes back as far as Da Vinci. Okay, and we can, I'm just going to keep plowing through this. We can recognize that so we've already established that we recognize that there's a complex interplay between interrelated metabolites. And therefore, the key point for this slide then is that if we recognize that there is this complex interplay between metabolites, it's not just the concentration or abundance of the peaks between groups that's important. It's the relationship between the metabolites that's also important, okay? And network analysis has been used loads of times in other metabolomics, but it's not really been applied to sort of breath data before. So this was really exciting. And so we already had confidence in the data that it contained these sort of communities, if you will. And we know biological networks possess this community structure property. And so we use Louvain clustering on top of the network to show us if there's natural communities within these metabolite sets to sort of validate what we're seeing in the metabolite enrichment analysis. And so this is a network graph. This is actual data showing the VOCs clustering. Each node represents a VOC, so one of those 101 VOCs, and the color represents the community that it belongs to within that network. And so one thing that's really neat with this is that we can sort of pull that cluster to one side, and we can look at all the chemical structure of all those nodes. And what we see is that it matches perfectly with the metabolite set enrichment analysis that we're doing. So this was quite involved. We gave it a lot of information. This was more natural and it was completely different, and shows natural structure. And the communities are a lot broader, but they encompass the same metabolite sets that we were seeing. So this was really nice. And so we now have a signature that reflects the complexity and the relationships within those markers in breath. And it still maintains clinical utility as well. So I don't know how I'm doing for time. Okay, so this will take like 10 seconds. So moving on then to the validation of this. If this data's structure is real in our breath data, we should see changes over time. And so we sampled the patients 6 months later when they'd fully recovered, and we took into account readmission. And if you look at the breath score from visit 1, so acute exacerbation, to visit 2, which is recovery, acute control. So this is really fresh data, like hardly anyone's, well, no one's seen this. We can see that the acute decreases over time, which is what you'd expect. And if you break that down based on subgroup, we also see that consistency. So the red here, the healthy controls, sort of remain consistent, and everyone else sort of goes from this acute state to this recovered state, which is really nice. And the final last thing, I forgot to include the p-values on this, but these are significant changes. Is much more minor when you look at an individual subset of it, but we still see that change in the metabolite clusters that we're seeing. So in conclusion, we've done some rock and roll stuff with GC breath data, and if there was one point that I want you to take away from this is really the last one. And it demonstrates that GC has an important part to play in the discovery of complex relationships. We always bang on about complex separation mixtures, which is true. But what that allows us to do then is discover complex relationships. So I think I'll leave it there. Thank you.